And here we are. There we go. In fact, it's not just data abstraction. This is the data abstraction talk. Why is it called the data abstraction talk? It's because it's a topic that keeps coming up. I'm doing this for a variety of reasons. Data abstraction is either one of those things that you heard about, but never really understood, or you were motivated to use it, but none of your colleagues appear to use it. Or it's just one of those habits that you never quite picked up, and you've never fully understood the mental model. And the problem is that a lot of the advice that we're given is handed to us as you should do this or not do that. And that's not very helpful. That's not constructive advice. It doesn't tell you how to build software. If I tell you you should make your data private, then you make your data private if you're following the rule. And does that mean you've got good abstraction? No, not at all. Look at most software and you'll discover that private is not deep enough. So you've not been told the deeper message. You've not been allowed to connect the dots. So this talk is either a reminder or it's a way of gathering all these thoughts into one place so that we really understood it. There's absolutely nothing new here. It's kind of a reminder. I want to just get a thread of thinking. So you walk away with a mental model. And often this came out because I said to people on Twitter or X, whatever. In fact, speaking of which, here's my social details. Referring back to what Dylan said this morning, it's fragmented to the point that I've just put everything up. I just used to introduce myself as @Kevlin Henney. I've given up. Twitter is my X. So I am contactable in a number of places. And I think it was on Twitter, but it could have been on Mastodon, where there was a discussion, and I sort of said, right, well, here's how to do the data abstraction thing. Maybe I should do a talk about this. Here's the talk. So we're going to start off by going to Mars. There's a very simple reason for this. One of my favorite interplanetary probes is Mars Curiosity. And yes, I do have favorite probes. I have favorite space stations, the whole thing. And one of the things about Mars Curiosity is like 1 ton of awesomeness that landed on Mars over 10 years ago. And its offspring, Perseverance, did so a couple of years ago. The code was written in C99, for those that care, and the approach that they used was very interesting. There's actually a whole article on this. But what I want to do is just describe from Gerhard Holtzman, who is the chief engineer of software. He made some very simple observations in talking about all the detail. He said there are standard precautions that can help reduce risk in complex software systems. So there's a couple of things here that I think are worth noting. First of all, he's not talking about eliminating risk. It's about reduction. You're never going to get rid of risk. But the point he's talking about is we can't guarantee everything's going to work, but let's reduce the probability that bad things happen. This includes the definition of a good software architecture based on a clean separation of concerns, data hiding, modularity, well-defined interfaces, and strong fault protection. That's 5 key characteristics. One of these is specific to the class of software we're dealing with, strong fault tolerance. Because if something goes wrong with your probe, you can't just send Matt Damon off to Mars to hit the reboot button. Okay? That's clearly specific. But the other 4, clean separation of concerns, data hiding, modularity, well-defined interfaces. Separation of concerns, data hiding, 1970s. Modularity, well-defined interfaces, 1960s. These are not new ideas. But just because they're not new does not mean we know how to apply them and what they mean. When we start talking about things like abstraction and hiding implementation details, what does that mean in practice? Or rather, what does the opposite mean in practice? Okay, given that we're going back in time, I'm going to take you back to the 2000 and teens. Okay, 10 years ago. And, oh, look at that. Implementation detail. Now, for the rest of the population, this is an arbitrary large number. But not for software developers. You're looking at that and going like, well, that's 2 to the 31 minus 1. That's the maximum value of a signed int on a number of platforms. That's not an arbitrary number. That's something didn't get initialized correctly. But I mean, this license will expire in 2 billion days. I'm good. I never have to give Microsoft a penny again. Fantastic. Except, apparently, my license has gone stale. Apparently, my license will expire long after human civilization has expired, but it's stale. That tells me that there's a difference between the presentation logic code and the representation, that we are using different languages and different type systems, because that comparison should be absolutely fine. So I've learned something about the implementation detail. Here, I have learned that in 2018, there were a number of ATMs that were still using Windows 2000. Here, we learn that Canada Post uses PHP to print out labels. And we even get an insight into their object model, which is kind of fairly rudimentary. If I take you back to the 2000s, and you can tell it's the 2000s because Firefox doesn't exist yet. There was a browser called Mozilla, and I used to use that. So I was visiting a friend of mine in the Netherlands, and I wanted to catch a train, but apparently I couldn't get an earlier train. I could only get java.lang.nullPointerException. So we know that this is implemented in Java. In fact, we also know it's implemented in Java because it says servlet up there. In other words, there are all these people who are quite happy to publish. Here's how we built the system. It's, oh yeah, we're following really good practice. We're keeping everything encapsulated. No, you're not. You've got .jsp, .asp, .whatever in your URL. You've just published your implementation technology. By the way, they've updated. It's good. They use JavaScript now. So the point here is when we start talking about things like abstraction, we often think in terms of the hardware. We often use the language of abstraction. We say, that's too low level. We abstract. This still feels a bit low level. We abstract. Let's move to assembler. Then I've got here's the C++ code that generated, yes, all those ones and zeros that is actually from the binary. So we've got that. This is a higher level view. I can give you a higher level view still and abstract it further. What we've got there is a stack. Hopefully you've had your breakfast and not salivating at this. But there's a thing here. When we talk about abstraction, what do we mean? So let's go to the dictionary. The result of abstracting, that is what an abstraction is. The idea of something which has no independent existence, a thing which exists only an idea. We are creating ideas. Importantly, it's opposed to concrete. We see these as opposites. Okay, so it's an idea of something. Importantly, it involves removal. Let's have a look at something that involves removal. So here's a payment card number. The first thing that we need to understand about removal is, here's a question. What is the hardest problem in computer science? Naming things, a good suggestion. Off by one errors. Oh no, they're really easy. Guaranteed single delivery. Guaranteed single delivery. And removing spaces from payment card numbers. Apparently this is a really big problem. I encounter it regularly, even in the 2020s. Apparently, it's easier to write error handling code to tell the user to remove spaces, to detect that there are spaces, to detect that it's wrong, write special extra code, and then tell them to do this rather than do the right thing. Apparently that's easier, or somebody's getting paid by the line of code. What we need to do is literally abstract the spaces, but there's a reason I'm focusing on this one. How do we represent this? A lot of people look at things and they go, oh, that's an integer. Let's use int. It's not going to fit that one. Yeah, that was a 16-digit number. We're not going to fit. Let's use long, 64 bits. That takes that. Let's use that. There is a small problem. And by this, I don't mean this. I mean the fact that most of these things are not numbers. You've been deceived. And all of them, they were deceived because it has number in the name. Payment card number. ISBN, International Standard Book Number. PIN, Personal Identification Number. You have been deceived into thinking these things are numbers because they're called numbers. They're not numbers. They are sequences of characters with constraints applied, and sometimes they just have digits. But if you look carefully, you will find that many things that call themselves numbers also have letters. So, yeah, you've got to look a little more closely. So, these are not numbers. We can hold them in a string. But of course, we need to remember to get rid of the spaces. Don't forget that bit. We can match them. It turns out that when it comes to payment cards, there's a number of standards. You also discover that if 19 digits is allowed, it won't fit in a long either. And it's actually partitioned. There's actually language around this. This is not just a bunch of digits. It's not just a number. There are sections to the number that have names and concepts. The last digit is a check digit according to the LUN algorithm, which I've rendered here in Python. So basically, you may say, oh yeah, it's a string. But it's a string where you have to apply these operations. Wherever you go, you have to apply these operations. So actually, it's not a string at all. It's what I've been saying all along. It's a payment card number. That's the name of the class. What we suffer from is that most systems that we work with are stringly typed. Okay? What you have is a primitive type, it's a primitive obsession, and a gathering of operations. And sometimes they are as tidily organized by name. More often in code bases, what you find is, oh, it's that string again, let's validate it. Didn't we validate it over here? Yeah, but you can't trust those people in that team. Let's validate it again for ourselves. And you end up with this amazing duplication. I visited a client many years ago. It was a Java code base, and I remember looking at the code base, constant validation. Let's just check the reference is not null. Let's just check that the data is in good condition. Let's just check. If you'd asked me what this system did, I wouldn't say, oh, that's a mortgage system. I would say, what this system does is it validates stuff. It mostly has if statements and a lot of duplicate code. So, this is where we want to be. So, if we're going to be there, what does that look like? What we're talking about here is an idea. It's a book I put together a few years ago. There's a piece from Dan Terhorst North, Code in the Language of the Domain. That's what we're trying to get at. That's the abstraction. We're trying to abstract. Abstraction is removal. But in one sense, we're not just removing arbitrarily, we're trying to remove in order to make something clearer. And in fact, we're adding something. A good abstraction is actually an addition. We are imposing our ideas. Remember, abstractions are ideas. We're trying to create a model of communication. This is not a new idea. Pattern languages of program design. This book collected together papers from the early patterns communities. This was published in the mid-90s. And there's a pattern from Ward Cunningham, whole value. Besides using the handful of literal values offered by the language, numbers, strings, true, false, and an even smaller complement of objects normally used as values, date, time, point, you will make and use new objects with this pattern that represent the meaningful quantities of your business. Construct specialized values to quantify your domain model. Make sure these objects capture the whole quantity with all its implications beyond merely magnitude. By implications, we mean how do you actually use it? More importantly, how do you use it correctly? And let us prevent you from using it incorrectly. And there's an additional observation. The word value here implies these objects do not have identity of importance. You do not rely on comparing references. Two objects that have similar content are considered to be equal, whereas entities are not considered to be equal in this way. We see this echoed in Eric Evans' domain-driven design book. That's 20 years ago this year. The value object pattern. When you care only about the attributes of an element of the model, classify it as a value object. Make it express the meaning. Notice this is all about meaning and communication, and give it related functionality. Treat the value object as immutable. Don't give it any identity. Now, the point here about immutable is important for a number of reasons. Most of that's a separate talk. But immutability is one way of preserving what we call an invariant. Slightly confusingly in English, invariant is also another synonym for, it's a synonym for immutable. But here, when we say invariant, we're saying rule. What is the rule that governs an object and its state? The rule that governed the payment card number was that it had particular content and particular relationship between its parts. If you violate that rule, then it's no longer a valid payment card number. So let's go back to our friend the stack. I'm going to render this one in Python. What I've done here is I basically said, so for those of you who don't read Python, there's a convention, you make everything explicit, including your this reference, but you don't call it this. You call it self by convention. You can call it this. Everybody in the Python community will look at you and just go, what are you doing? I don't understand the code anymore. You're no longer part of our community, and they will eject you just for spelling that this. So just so you're aware. But what we've decided to do is just add in an attribute, add in a field. We're going to call it list. This is such a common habit. Well, there's two habits here. One, what they've done is they've made it public. They've made it directly accessible by its raw name. Everybody can go and look at this object and say, show me your internal list. The other thing is they've named it after its type. Absolute genius. Who said naming was hard? Yep, you're right. So here we've got this behavior, and then I come along and I say, well, I'm not really comfortable with that name. I prefer to refer to it as the items rather than the implement. So I'm going to rename it. What is the consequence of doing this rename? You break every single piece of code that depends on it. Brilliant. So that is a syntactic breakage. There are other kinds of breakage. Let's look at this one. In its current implementation, I'm using a list. The last element of the list is the top of the stack. When you append, we're going to say that's push. So it's at the other end. I could invert it. I can make element 0 the top. This is semantically equivalent as long as all my operations agree. So if I go ahead and I make this change from that to that, I haven't changed the data representation. I have changed the protocol for using it, such that when I take what was at the end, if I say that here's our assertion, here is a truth of the implementation, the last element, by the way, -1 counts backwards. It's a great feature. A couple of languages have it. I wish more did. That's the top element. So imagine we have an undo list. It's the most natural observation or example of a stack that we have. Okay? It's not just an arbitrary abstract data type. Every time you have an undo list, it's stack ordering. So I'm going to take that, and now I'm going to apply that refactoring, and we're going to find that it goes from green to red. You've just broken every single piece of code. This is a semantic change that was syntactically compatible. What we've got here is an assumption, and we've just broken assumptions. So let's go back to 1983, to the first reference I've been able to find to the idea of the contract metaphor. From Butler-Lamson, an interface is a contract to deliver a certain amount of service. Clients of the interface depend on the contract. Your contract is not just a set of assumptions. It's not just an arbitrary publication of we just felt like this on a Tuesday and changed our minds on a Wednesday as to how to implement it. It's actually, you can rely on this. What you're doing is you're offering somebody a literal contract. If you behave in this way, I will support that. I will support your code. Okay, now it gets really interesting. We've got this approach, but what if I refactored it as a singly linked list? I can do that. I can take it from here to here. That involves both kinds of breakage. I've renamed it. It's no longer items, it's the head. We're now referring to the head element of the list. And the structure, the semantic, everything's changed. So, let's go back 30 years this time. Design patterns. 2023 is clearly a very significant year. There's lots of even decades we can run off here. Amidst all the other advice in this book, one of the simplest and most often quoted is program to an interface, not an implementation. Which is ironic, given that this book brought Singleton to the world, which ends up programming to an instance, not just an implementation. But that's a separate rant. The idea is the interface. What is the interface? That's the interface. You can construct it, you can call depth, you can call top, you can call push, pop, and these have consistent behavior that we can verify with tests and publish with tests. I can do this, but now I've shifted the name. I've shifted the name so it's not, that name is not publicly accessible. That name does not exist in public. I'll come to the small caveat on that. This is done by convention. So the idea in Python that things should be explicit, better explicit than implicit, that's not really true. There's a whole load of conventions. Every language has its little conventions, some of which are enforced more strongly than others. But now I can freely work to that interface, and I can change, I can invert the thing, I can replace it with a singly linked list. If anybody tries to refer to that member by its name, they will get an attribute error. They will get a runtime error that is based on the type system. That name, however, is actually based, it does appear, or rather, the attribute is available under a different name. There's a bit of name mangling that goes on. And the name mangling allows you to access that name if you want, but it's done in a way that makes it ugly. So you can spot when somebody's doing this. It's intentionally there. So the idea is it's kind of like a soft form of hiding. Yes, you can access that value, but you can't use the name __ head. You have to use this unwieldy name. And notice, and you will notice, you can probably look at your own code base, you will notice your class names are not small. Yeah, something happened around the year 2000, and class names started getting ridiculously long. There was a sort of abstract factory manager, singleton, blah, blah, blah. And people just started gluing things together like Lego bricks. So the great thing is you can really spot somebody trying to access stuff they shouldn't be touching in the code. But normally when we use the term encapsulation, we have a stronger idea in mind. And quite literally, encapsulation means to enclose in a capsule. In fact, the dictionary highlights that it goes further. To summarize, in other words, capture the essence of, or isolate. Isolation, now this is getting interesting. So when I said this stuff, data abstraction, this goes back to the 1970s, primarily it's anchored in two papers by David Parnass. It's got this snappy title on the criteria to be used in decomposing systems into modules. This is 1972. And he makes the observation, these are the benefits of modular programming. By module, he means perhaps if you're thinking, Python modules, or if you're thinking Java modules, no, it's not really those. He's thinking anything that is a unit of modularity in any language. And sometimes even if it's not supported by a language, we can say, yeah, modules. So a class constitutes being a module, just as a file that has by convention public and private parts, or an assembly or a component that has public part and private parts. 1, managerial. Development time should be shortened because separate groups would work on each module with little need for communication. Product flexibility. It should be possible to make drastic changes to one module without a need to change others. Comprehensibility. It should be possible to study the system one module at a time. In other words, you don't have to know everything in order to make progress. If somebody gives you, if you're working on a code base of 1 million lines, it should not feel like 1 million lines. You should be able to say, I have to know my local area, but I only have to deal with these interfaces. Those modules, I do not need to know anything about their implementation. No abstraction leakage. By the way, this feels kind of like fresh. Okay, this is over half a century old. Feel free to copy and paste this slide and just change the words to fit your context. The message has not changed. We're still trying to do this. In another paper published that year, he actually really introduced the idea of information hiding, which was you should not have to publish all the information about how things are built to other developers. That's for the implementer of something. We make a separation. But we need to worry about dependencies. The connections between modules are the assumptions which the modules make about each other. It's not just the things the type system will check for you. It's not just what you look at in an IDE. When you look at an IDE, it'll show you your dependency graph. No, that's not your whole dependency graph. There's all the other little conventions and things that if you change something, something else breaks. So to really appreciate that, here we've got something. Let's say it's defined by its data. Maybe it's that stack class, and we've decided that we're going to make our data easily accessible to everybody. And here's our immediate dependencies, and here's the transitive dependencies. And then we come along and we decide, you know what, we're going to change something. First thing that happens is breakage. This is syntactic breakage. If we change something about the syntax, it's a syntactic breakage. But I'm actually going to change that word, syntactic. Syntactic breakage is structural breakage. Syntax makes it sound really small. Structure makes it sound really big. That's because it is big. Syntax is a way of saying, does this plug fit into this plug? Semantics is a way of saying, does the right signal travel across it? Those of you who've seen the Star Wars movies will know that R2-D2 at one point plugs into something, and that's wrong. It turns out he gets fried. Yeah? Do not design plugs and sockets like this. The idea is the semantics of that connection were wrong. But here we're just talking about syntax. Now, what we'll find, depending on the way that your type system is checked, if it's a dynamic type system and it's dynamically checked, then that's the level of breakage. If, alternatively, the boundary that we've got there is you're inside a process, when you go from one process to another, you change type systems. It turns out that the network doesn't really care about stuff because it's mostly byte-oriented or stringly typed. So you change type systems. So you can actually have the wrong types in two different processes unless you have a common build system. Actually, even if you have a common build system, you can still mess it up. If you're in the same space, though, and you're using a statically checked language, boom, everything breaks. OK, let's try something different. Let's separate the concerns, the concern of representation, how I choose to represent my data, from how I intend to use it, the interface. I'm going to treat these as two separate constructs. And now we reintroduce the direct dependencies and the transitive dependencies. I make a change to something that is semantically compatible. Nothing breaks. Isn't that fantastic? How do you know that something doesn't break? Because you've got tests. And if you're sitting there going, like, we don't have tests, that's another talk as well. In fact, it's not a talk. It's a week-long workshop with therapy and tea. If you change anything about the contract, however, then depending on whether it's a syntactic or semantic change, tells you how much stuff you break. So the idea here, every module is characterized by its knowledge of a design decision, which it hides from all others. Its interface or definition chosen to reveal as little as possible about its inner workings. Fantastic. Now, Venkat mentioned the similar language, 1967. First object-oriented language, okay, developed in Norway. And I wrote some code in Simula, just for a bit of fun. And here is a class. It's a stack. It's got a capacity, which is going to be an integer. There's a block. There's our representation. We are holding an array of references to pancakes. And we've got a count of how many things there are. And then we have a series of operations. These are embedded in the block. These are basically methods. And then we've got an initialization. There's no constructor. It's all done as kind of executing a block. A question you might have is, OK, that representation, the items and the count, are those public or not? I mean, this was the first object-oriented language. They are, in fact, public. The idea of making them private did not really get standardized in Simula until the mid-1980s with Simula 86. Notice the word hidden. So actually, prior to this was actually worse than the situation in Python. You just had to tell people, please don't touch that. Yeah, we know how effective that is. Yeah? Maybe you put a comment by, these are private, and then other developers looking at it going, no, they're not. I can see them. I can see them. I can touch them. I can change them. So there's a whole point. We're focusing a lot on this idea of the kind of the good properties and stuff like that. So this is a notoriously unreadable book. It's called A Theory of Objects. I say it's unreadable. I think it's got 5 or 6 sections. The first section is written in English. The remaining sections are written in Sigma calculus. If you struggle with sleep problems, honestly, I cannot recommend you anything better. You will find yourself asleep. It's published in the mid-90s. It's kind of extensive, but the bit that's written in English actually talks, mostly the book is about data abstraction. Object-oriented programming does not have an exclusive claim to all these good properties that we've been talking about. Systems may be modeled by other paradigms. Resilience can be achieved just as well by organizing programs around abstract data types. Sometimes people have heard of abstract data types, but they're not quite sure what they are. This is kind of an interesting thing because they don't involve inheritance independently of taxonomies. That's the idea there. In fact, data abstraction alone is sometimes taken as the essence of object orientation. For many people, that's the first thing they think about. And that's actually my own personal history. When I first discovered objects, whenever that was, a very long time ago, when I first discovered objects and came across this idea, I had been working in languages that had no concept of data abstraction at all. So for me, the most important thing was the data abstraction. But you don't need to have an object-oriented system. In fact, most people working in objects are actually working in ADTs. Now, where's this stuff, ADT, come from? Abstract data types. Barbara Liskov. Some of you may have heard of the Liskov substitution principle. Yes, it's her. She won the Turing Award in 2008, I think. For a mix of things, including her contribution to kind of programming methodology and programming language design. So this was, all that work was like early 70s, 1973 to 1975, 76. An abstract data type defines a class of abstract objects which is completely characterized by the operations available in those objects. You're thinking, yeah, this sounds really familiar. This is how I was taught objects. A programmer is concerned only with the behavior which that object exhibits, but not with any details of how that behavior is achieved by means of an implementation. Yeah, this all sounds really familiar. If you like, OO kind of moved into the ADT space and kind of ate its lunch and its breakfast. So a lot of people think data abstraction, that's an object-oriented concept. No, it's a concept that is common to many paradigms. To the best of my knowledge, this is the first stack. In fact, I cleaned it up a bit and corrected a couple of errors. It's kind of interesting correcting errors in papers that are nearly half a century old when you don't have access to the compiler. So this is the language clue, CLU. And this, to the best of my knowledge, is the first time stack appears as an abstract data type. So there's a historical moment there. And the representation concept is automatically private. You don't get a choice of exporting it from a module, because it's abstracted. So let me bring this home to something more familiar. C# programmers, raise your hands. Yeah, there's a few of you here. Okay, so let's see what a C# programmer would do for the stack. You'd write it like this, wouldn't you? Actually, no, you wouldn't, would you? Because surprisingly, a lot of people don't use expression bodies, even when they can. Okay, you'd write it like this. And people are going like, no, that's got a public field, Kevlin. What kind of idiot are you? We make our data private because, otherwise people can come along and just like replace our implementation. Oh, okay. Yeah. Yes, of course, I see how you've made it private. You've introduced an auto property that privately declares something that you cannot directly name, and then immediately allows you to get the value and also set it. So in other words, properties, in the way that most C# developers use them, are a long way of writing fields. It just makes you feel good that you're not writing a field because you've been told that that was bad. Okay, let's see what happens here. We can improve that. First of all, you can look, but you can't touch. We'll make that private. Okay? Brilliant. Now when I try and do this, this no longer compiles. Excellent. So now we cannot modify the internal state of the stack. And as an extra refinement, we can actually say it can only happen internally to the class at initialization. A couple of people are nodding their heads. Yep, this is how I'd implement it. Well done, you have just reinvented read-only fields. Congratulations, but you've got more syntax, so it makes it look like you're doing work. Okay? Let's understand what's happening here. First of all, what is the top element? The top element is, well, also, programmers love to chain all this stuff together. Honestly, just, make people's lives easier, abstract. So that is at the last from the end. Okay. So that's that implementation. What happens if I flip it upside down like I did with the other one? Well, suddenly our top element is now, the 0th. Congratulations, we have just broken every single piece of code that depended on it. Yeah, it's a semantic breakage. So that's unfortunate, because we've effectively published an assumption which way we're indexing. So we've got this thing. I'm going to add a constraint just to make it a little more interesting. I'm going to introduce an invariant that is not simply our list field, our private, should be private, but our representation should not be null. I'm going to introduce another constraint. Its contents should not be null. In other words, the content of this stack, there should be no null references in it for nullable types. And I've got that enforced on entry. Okay, how does this work out? This is the invariant. Okay, an invariant is a statement that is true. I'm basically saying this is true for everything. There are no nulls in this stack. That is what it means to be a stack. Just like a valid payment card number, this is what it means to be a valid payment card number. It's only digits, and the last digit conforms to a check digit calculated from everything else. There is no possibility that once you have correctly constructed one of these that you are able to violate that invariant. The idea of encapsulation and abstraction, information hiding, separations, is that once you have said this is good, you defend it. You put a barrier around it and say, yep, you don't need to worry about this. It works. You constructed a good object and it will remain good for as long as the implementation is correct, for which you have tests, or a week of tea in therapy. Okay, so how are we doing? Let's go back to that and let's just assign one of the elements to null. Oh, that was easy. We just violated the encapsulation. We just bypassed that. This is what most... So here's a kind of a simple thing. If you see collections in your public interface, if you have properties that are collections, if you have methods that return collections, there is a very high probability that there is a violation of encapsulation. I consider it actually a code smell. It's one of the things my eyes scan for. Oh, you're returning a list here. Do I know if that's a copy or not? Because it's probably an implementation detail that you've decided to publish, even though the field might itself be private. In fact, it's so private, it's an auto property. So let's actually fix this design and understand how we should have done this. I'm going to keep the read-only, because honestly, it was a perfectly good list at the construction. I don't see any reason to get rid of it. I'm going to use that. But Kevlin, how do I get access to the elements? That's why people do this. But that's an overcommitment. You've over-published the interface. Well, here's a simple way. Publish an indexer. You know, you can refer to element 0, 1, 2, and whichever way it's been implemented, it always respects the semantic rule. You have a contract. And you can refactor to your heart's content internally. You can have a linked list. You can have a list go forward. You can have a list go backward. You can do whatever you want. But as long as this contract is respected. Alternatively, or in addition to, what you're doing is you're publishing views. The idea is like, oh yeah, you can traverse this, and I will show you this value. We can go a step further. If you want a property there, then what you do is you publish the interface that you control. And you tell people what they can do with it. You don't publish a list. That's a very strong commitment. What you do is you say, if you would like to enumerate the members, here is a way of doing it enumerably. In fact, you might even make the whole thing enumerable. And that is the trick. That actually, interestingly enough, so we can now actually guarantee that this is going to be the case. What we have here is the interesting observation that goes back to something I said as a throwaway comment, which is immutability. The stack is not immutable, but what I've done is I've restricted your ability to access the mutability. You can't modify this except through its operations that you have chosen and published and tested. Now, if we're going to publish and test everything, of course, you need to kind of respect a few things. There is actually a term Martin Fowler coined in his original refactoring book, and he followed it up with an article a couple of years later in his IEEE software column on public versus published interfaces. The idea is that a published interface is something that is out of your control. That's often the case when we give something to if we publish something on the web, if we're publishing things in open source projects, if we are publishing something to another team in another company, or even within our own company, where if we change something, we don't have access to their source code. And therefore, if we change something, we break theirs. It turns out that, published is quite difficult. Published you need to be careful with. So he offers some guidelines. Don't treat interfaces as published unless they are. Don't publish interfaces inside a team. That's important. If you are in a team, then all of you should have access to all of the source code all of the time. We might say we want to extend that beyond the team, but let's just work from a simple point of view before we generalize and extend that. What this means is that if I create a class, if I create some kind of module with a set of functions, and I offer it to my colleagues, and then tomorrow I think, you know what? That interface sucks. Or my colleagues have told me that interface sucks. I'm going to change it. If it were truly published, then I'd say, sorry, you're stuck with that contract. Software should be soft. Inside the team, you should be able to refactor at will. And importantly, so in other words, publish as little as you can. Now, there's an interesting consequence to this. Often people talk about the open-close principle. I'm not going to talk about it at length, except to say it's widely misunderstood. It was originated by Bertram Meyer. In its popularized form, it's misunderstood. He was actually saying something completely different, and what people think is OCP is not OCP. That's a separate conversation. The idea that you should make something open to extension, I think it's a consideration. I think it's not a general principle. You should not be doing this for all of your code. It's a terrible idea. We've seen what that looks like. It's everything's generalizable. Everything. No, don't. Things should not be open for extension as a matter of principle. It's a matter of consideration. And then there's this other one that people are utterly blind to, but I always draw people's attention to it when they say, oh, Kevlin, you're criticizing OCP. And I said, right, tell me why your code should be closed for modification. Yeah? Is it a principle that you write a class and then you cannot modify it? That's a terrible idea. In fact, the only time you ever want to apply this is in an interface that you have published. At that point, it is pretty much closed for modification, except additive modification or deprecation. In other words, OCP is a failure mode. If you are telling people you can't modify this, that's a failure. What you're dealing with, we have a name for this. It's called legacy code. Legacy code is closed to modification. I mean, even though there are management requests to change it, you're looking at it and go, I don't want to modify that. I don't know how to modify that. I fear modifying that because I have no tests. So in other words, you don't want to use OCP. Use OOP instead in this context. The idea here, and obviously when I say use OOP, I mean basically any form of data abstraction, but data abstraction didn't fit the slide, so I just kind of summarized it here. So that brings us to this observation. The purpose of abstracting is not to be vague. Sometimes people think abstraction is about high-level waffly stuff. It's like, no, it's not. It's about creating a new semantic level in which one can be absolutely precise. This is what this idea is. It's not a bunch of strings and integers, and please don't touch the list. Oh, and there's a comment that says, yeah, don't put nulls in here. We can do that. We actually have language features to do that. I still remember years ago seeing a piece of code that had the most important low-level feature was a public member. And there was a comment by it saying, please do not modify. And this was in a language, and it was right below the public. It was right next to the public keyword. I've made it public, but I don't want you to actually treat it as public. In which case we spell that private. And we go further than just private. We hide the implications of that and the ability to subvert that concept. Work with the abstraction, help other people work with that abstraction. Thank you very much.